In this lecture, we are going to discuss about some theorems on continuous mapping in a matrix space. Let f from x to y be a mapping where x and y are matrix spaces. Then f is continuous at x naught if and only if xn converges to x naught implies f of xn converges to f of x naught. F of x proof. In the statement of the theorem, it was given f from x to y via a mapping xy are matrix spaces. F is continuous at x naught, then so this one. And if this hypothesis hold true, then so f is continuous at x naught. Let first let f be continuous at x naught and xn converges to x naught. Since f is continuous at x naught, our aim is to show that whenever f is continuous at x naught, then fn converges to x naught implies f of xn converges to f of x naught. Since f is continuous at x naught, for epsilon greater than 0, there exists delta greater than 0. So step for all open sphere, as epsilon above x naught, there exists another one as delta x naught, such that f of s delta x naught is a subset of s epsilon above x naught. Since xn converges to x naught, by definition of convergency, for this time I'm not going to take epsilon greater than 0, but I will take delta greater than 0 in order to get our required result. There exists some n naught belongs to m such that xm belongs to uh, s delta s delta x naught for all n greater than equal to n. This is from the definition of convergency of the sequence. If I take f image, then this is f of xn belongs to f of s delta x naught for all n greater than equal to n. Since s delta x naught is f image of s delta x naught is containing this s epsilon f of x naught, that means this f of xn ultimately belongs to this s epsilon f of x naught after some n greater than equal to n. Okay, this implies f of xn converges to f of x naught. Okay, that is first part of the theorem is proved. We are going to prove the second part. We are going to prove second part. For second part, conversely, conversely, we shall assume that we shall assume that not continuous at x naught, then we shall show that we shall show that fn converges to x naught but does not imply above xn converges to above x naught. Since f is not continuous, f is not continuous at x naught for all open sphere as epsilon above x naught, there exists another open sphere as delta x naught, such that since f is not continuous at x naught, f image of s delta x naught is not a subset of as epsilon above x naught. Okay, so let us consider the sequence of open sphere with radius 1 by m x. Then we can form a sequence. Then we can form a sequence xm such that xn belongs to the open sphere as 1 by m x naught. But since f is not continuous, f of xn does not belongs to this sphere. Does not belongs to this sphere as epsilon above x naught. Okay, no, above x. This implies f of xn is does not converge to f of x. Then for epsilon 1 greater than 0, since there exists some and not belongs to the set of natural number, since that epsilon 1 is greater than 1 by n naught, xn belongs to s. Now this is epsilon 1 s naught for all n greater than equal to n naught. Since epsilon 1 is greater than 1 by n naught, if I take this reverse, okay, this implies xn converges to x naught, but from here f of xn does not converges to above x naught, which is a contradiction to our hypothesis. Our hypothesis is whenever xn converges to x naught, f of xn converges to f of x naught. And this contradiction arises because we have considered f is not continuous at x naught. Therefore, f is continuous at x naught. This is a contradiction. This is a contradiction. Contradiction. Hence, f is continuous at x. Next, we are going to discuss definition of continuity in the matrix space. So, next definition: let f from x to y be a mapping, be a mapping, be a mapping, and is continuous, if it is continuous, if it is continuous, it is continuous at every point of its domain. Okay. Next is a theorem. Next is a theorem. Let f from x to y be a mapping where x and y are mapping spaces. Then f is continuous if and only if f1 converges to x implies f of xn converges to f of x. This theorem, proof of this theorem is exactly same as the last theorem that we have proved here. Only difference is that in the beginning of the theorem you should write let x naught belongs to x be an arbitrary point. Then you should write the proof of the last theorem. After completing the proof, you should write since x belongs to x naught belongs to x is an arbitrary point of the domain, so f is continuous at every point. Hence, f is continuous in the matrix space X. With that, your proof will be complete.